Right, so in this video we'll be talking about using complex numbers to solve AC circuit problems. Okay, so you have to really pay rapt attention to this portion of the tutorial video. Okay, they sometimes sound confusing, but they are very simple. Okay, right, so we'll be dealing with what solving complex numbers, using complex numbers to solve AC circuit problems with respect to impedances, and then what with respect to power. Okay, so the first topic would be based on what impedance. Okay, and then the second one will be based on what power. Okay, so in case you are new to this channel, kindly subscribe, hit on the bell icon so that you don't miss out on any uploaded videos. Like the videos so that they get pushed to other students who might need this video. Let me know your questions in the comment section, and then don't forget to share to your colleagues. Okay, right, so let's look at what for impedances. Okay, so for impedance, the first thing you need to know is that the I in complex numbers, okay, is being represented with J, so that it doesn't what confuse you when it comes to what current. Okay, so maybe when you meet this I and then the current representation for I, it doesn't confuse you. Okay, that's why they are being replaced with what J. Okay, and then for impedance, the R remains the same. Okay, but for the opposition to inductance changes to what JXL, and then same applies to what capacitance, but a little change. Okay, that's where we have what a negative sign. Okay, and then we have JXC. Okay, so now, right, so these are the things you need to know. These are the main points you need to know. 1, 2, 3, 4. Okay, now let's proceed. So for series impedance, we have the impedance is equal to R plus J. Okay, then we have XL, opposition to inductance, minus the opposition to what capacitance. Now let's take this example and then we proceed from there. Okay, so we have to express in rectangular and then what polar notation the impedance of each of the following circuits. Okay, at a frequency of what 50 Hz. Okay, so resistance of what 20 ohm, resistance of 20 in series with inductance of 0.1 Henry, and then resistance of 50 in series with what capacitance of 40 mFarad. Okay, so we are using what this formula. Okay, right, so let's proceed. It's very simple. Okay, so we have a solution. So first we write the formula out. Okay, so Z equals what R, okay, and then plus J, then we have what XL minus what XC. Okay, so for question A, we have only resistance of 20 ohms, so all of this goes to 0. Okay, so we have what Z being equal to what only the R. Okay, that's 20 plus, okay, this goes to 0, so you have 0J. Okay, so you can just punch this straight on with your calculator, and then you get what in polar form. So this is the rectangular, we are now converting to polar. Okay, so for polar form we have what 20 and then angle of 0 degrees. So you can punch this on your calculator. I've already taught you how to do this in complex algebra, so you just have to follow the procedure. Okay, so now let's look at question B. So we've been given resistance of 20 and then inductance of 0.1. So we have what Z. Okay, so resistance of what 20. Okay, and then plus what J of what inductance of what 0.1. Okay, right, so for XL we need to calculate. Okay, and then we have what SC. Okay, right, so now let's calculate for what XL, because we were given only L. Okay, so XL we have what 2 pi FL. Okay, that's what 2 pi 50 times what 0.1. That's what, when you compute this, you get what 31.416. okay, 31.416 ohm, right? So this is how it goes. So we have our what? Z to be equal to 20, okay? We don't have XC, okay? So we only have what? 20 plus 31.416 J, okay? And then when you punch this or convert this into polar, you end up with 37, okay? 37.242, okay? And then we have our angle of 57.52 degrees. Now let's solve the last question. So we have what? 50 and then what? Capacitance of 40 mil farad. Okay, so we have C. Okay, so let's find what AC. So we were given only C. Okay, so we have 1 over what? 2 pi FC. Okay, so that's what? 1 over 2 pi times what? 50. Okay, and then times 40 mil. Mil is 10 exponent minus 6. Okay, 6. Okay, so this will give us what? 79. Okay, 79.577. Okay, ohms. Okay, so now let's proceed. So we have Z to be equal to 50. Okay, note that our formula over here, okay, our formula over here is supposed to change to what? When writing in complex, supposed to change to what? Negative. Okay, right. So let's proceed. So we have what? Minus 79.577. So when you convert to what? Polar, you will get what? 93.981 with an angle of minus what? 57.86 degrees. Okay, right. So this brings us to the end of the impedance. Okay, converting what, or using complex numbers to solve AC circuit problems with respect to what? Impedance. Let's move on to what? Power. Okay, right. So let's move on to power. So for power, these are the two main changes you need to know. Okay, so we have S, that's the apparent power has to be equal to what? VI, but you could see that we have a certain asterisk over here. It means that you have to take the negative for the current. Okay, we will take an example so that you get to understand. Okay, so the same thing applies. So we have, for converting towards complex numbers, we have P plus J Q. Okay, so that's the general formula. Okay, now, so when Q is positive, okay, so Q is positive when the current lags the voltage. Note, whenever you meet lagging, it means that what? It's positive. Okay, whenever, and then whenever you meet what? Leading, it means it's what? Negative. Okay, so let's take another example. Okay, so these are the two key points or key notes you need to take into consideration. Okay, the apparent is equal to the VI. Okay, but the I has to be what? Converted towards or changed towards negative, and then the same thing applies to what the apparent is equal to what? The active power plus the J of the what? Reactive power. So you've been given a question. Okay, so we have what? The potential difference across and a current in a circuit are represented by what? This and that. Okay, so this is the voltage, this is the current respectively. So you have to calculate what? The power and then the reactive what? Volt ampere. So we are calculating power and then reactive volt amperes, and then we've been given what? This and that already. Okay, this is volt. Okay, volts, and then this ampere. So let's move on to what? Solving this simple question. Okay, so we have S equals what? VI, which is asterisk, and then we know that S is the same as P. Okay, plus J Q. Q. Okay, so now let's proceed to solving that. So from here we have what? Certain 100 plus J 200. Okay, you put that in brackets and then you multiply by the I, which is this one. Okay, so we have the whole of this is I. Okay, because it's in what? The unit is amperes and the whole of this is J. V, because the unit is what? Volts. Okay, so we have 10. Okay, plus J5. So now watch this. This is where the asterisk comes into play. Okay, right. So now we have 100. Okay, plus J 200. Okay, and then open bracket we have 10 minus. So you negate it because of this. You negate it. Okay, J5. Okay, so now let's see. When you punch this directly, okay, you have to punch this. So you multiply this with that. Okay, you just do your simple simplification. 100 multiply by what? 10, and then 100 multiplied by minus 5J. Okay, and then we have 100. Sorry, J multiplying what? 10, and then J 200 multiplying what? Minus J5. So when you do that simplification, you end up with what? 2000. Okay, plus J5 what? 100. Okay, so now, sorry, 1005. Okay, so now from here you could just notice that we have P and what? Q. Okay, because this is what? P. Okay, and this is what? Q with what? J over here. Okay, so this could be represented as what? S to be equal to what? 2000. Okay, plus J what? 1005, which is equal to P plus what? JQ. Okay, P is this and then J is that. Notice that this is really simple. Now let's move on to what? Okay, so let's see how we go about this question. Okay, so a small installation consists of the following what? Loads connected in parallel across a single phase 240 volts 50 Hz supply. Okay, and then we've been given what? A fan motor having an input of 2 kVA at 0.75 power factor lagging. Okay, and then a 1.5 kilowatt radiator operating at unity power factor. Okay, and then we have what? A 1 kVA loading operator. Okay, load operating 0.85 leading. Okay, take note of these points: leading, lagging. Okay, leading, lagging. Okay, they are very, very important. Okay, so we have to find what? Total current kW, kVA, power factor of the load. Okay, so let's dive right into this. Okay, now let's draw a table. Okay, so we have what? S. Okay, that's what? kVA. Okay, then we have what? Cos theta. Okay, and then we have what? Active power. Okay, which is in what? kVA. Okay, and then the formula for active power is what? S. Okay, cos theta. Okay, this S. Okay, that's our apparent power, and then we have sin theta. Okay, so sin theta from trigonometry, okay, is equal to the root of 1 minus cos theta squared. Okay, keep this in mind, and then we have our Q. Okay, so our Q is in what? kVA. Okay, kVA R. Okay, and then we have a general formula as what? S. Okay, sine of theta. Okay, right, so this is very important. Let's draw the line. Okay, let's draw these lines. Okay, right, so we first been given what? A 2 kVA with what? 0.75 power factor. Okay, so we have 2 kVA with what 0.75 power factor. Okay, note that this is our power factor. Okay, because theta is power factor. Okay, and then we've also been given 1.5. okay, so the second one is what 1.5. okay, with unity power factor. Okay, unity power factor, so we have what 1. okay, power factor is 1, and then we have third is what 1 kVA. okay, so 1 with what 0.85 leading power factor. Okay, so we have so bear in mind that since it's leading, it's what negative. Okay, right, so we have 0.85. okay, so now let's find what P. okay, so P is what S cos theta. So once you multiply S 2 by what 0.75, you end up with what 1.5. okay, and then you do same for here, you end up with what 1.5, and then you do same for here. So 1 multiplying 0.85, you will get what 0.85. okay, so right, so let's move on. So we have what S what theta, that's equal to what root of 1 minus cos squared theta. Okay, so when you punch this, so it's something like this. Okay, we have 1 minus this cos squared theta, so this is cos theta. Okay, so these are cos theta, so we have what 0.75 squared. Okay, so this is how it will look like. Okay, so when you punch that, you end up with what 0.664, 0.75 power factor, and then for 1 power factor you will get what 0, and then for what 0.85 power factor you will end up with what 0.527. okay, so when you punch 1 minus 0.85 squared, you end up with 0.527. okay, right, so let's move on to what Q. Okay, now for Q we are multiplying what this S value with what sin theta. Okay, so we are multiplying 2 by what 0.66, that will give us what 1.32. okay, and then you multiply 1.5 by what 0, and that will give us what 0. Then you multiply 1 by what 0.527. Note that since for C we have 1 kVA load operating at 0.85 leading, it means that our Q value will be what negative. Okay, so once you multiply 1 by 0.527, you get what minus 0.527. okay, right, so now let's find out total values. Okay, let's find out total values. Okay, so we have what total, for total of what when you compute all of P. okay, you end up with what 3.85. okay, and then you compute for Q. okay, we have 0.793. okay, so now you can go ahead and calculate total current, kW, kVA, and then what power factor and the rest. Okay, right, so now let's proceed. So we have our total kVA. okay, let's start from K. Okay, that's our power. Okay, main power, the actual power. Okay, or active power, that's what 3.85. this unit is what. Okay, right, so let's say total power. Okay, right, let's calculate for what our total apparent power. Okay, our total apparent power, that's S. So we have kVA. okay, and then we know that that's equal to what P squared. okay, plus Q squared. okay, so this will give us what the root of p squared. So we have p over here. Okay, so we have 3.85 squared, okay, plus our q, okay, that's 0.793 squared. So when you compute all of this, you end up with what? 3.93. okay, that's in what? kVA. Okay, so now let's proceed to find out what current. Okay, so since we know that S is equal to what? VI, most definitely we know that I is equal to what? S on what? V, okay, and then we know our S value is 3.93, okay, so 3.93, so we have kilo over here, so we have times 10 exponent what? 3, okay, divided by our voltage, that was 240, okay, 240, okay, so when you compute that, you end up with something close to 16.375 amperes, okay, right. So let's proceed to find out what our power factor, okay. Our power factor is equal to what? Cos theta, or the same as what? P on what? S, okay. So you know that our P, we've already calculated P to what? 3.85, okay. From here, so we have what? 3.85, so that will be divided by our S. So we know S to be 3.93, okay, 3.93, and when you compute that, you will get what? 0.980 lagging, okay. So this brings us to the end of this video. Kindly subscribe, hit on the bell icon so that you don't miss out on any uploaded video, and I will see you in the next video. Bye bye.